We can think of the effective porosity of a porous material as the volume of pores that are important for flow to the total volume. That ratio is the effective porosity, and here I'm writing effective porosity as N sub E. Now, if we want to measure the effective porosity, it's really not feasible to measure the volume of the pores that are important to flow. So instead, we use this definition for the effective porosity, and that is that the average velocity of flow through porous material is equal to the volumetric flux divided by the effective porosity. So that means that the effective porosity is going to be equal to the flux divided by the average velocity in that direction. The average velocity is greater than the flux in porous material, so the effective porosity is going to be less than 1. And in fact, if this is the volume of pores that are important to flow, not all of the pores in porous media will be used by the flow, and some of the pores will be dead-end pores, for example, or some of them will be too small to support flow. So the effective porosity will always be less than the total porosity. If we want to use this definition, then what we need to do to determine the effective porosity is to measure the flux and the average velocity independently. The flux is determined as the flow rate per unit area, and the velocity is determined using the travel time over a unit of distance. That's usually done by introducing a tracer into the porous material. One important aspect is that the average velocity, which we want to know for contaminant transport analyses, is going to be determined using the effective porosity, and we can take one step further and estimate the average velocity this way using Darcy's law. So the hydraulic conductivity and the head gradient are fairly straightforward to measure, and if we can then estimate the effective porosity, we can determine the velocity. So one reason for wanting to know the velocity is to estimate the travel time. And the travel time is how long it takes a particle of water or material moving with the water at the same pace as the water, how long it takes to travel from over a unit of distance. So the average velocity equals the time that it takes to travel a unit of distance. So the travel time then, delta L, is just the distance divided by the average velocity. Let's call that V bar. Okay, so if we have a problem like this one where the volumetric flux in a poorly sorted sand is 0.05 meters per day, the effective porosity is 0.1. How long does it take for the water to travel 100 meters? So if the flux is 0.05 meters per day and the effective porosity is 0.1, then the velocity is going to be equal to the flux divided by the effective porosity. So that'll be 0.05 meters per day divided by 0.1, which will be 0.5 meters per day. And travel time will be equal to the distance divided by velocity. So that's going to be 100 meters divided by 0.5 meters per day. And that'll be equal to 200 days. That's how long it takes water to move over this 100-meter distance.